Okay, team, as a quick reminder, we will be recording this session today, and so just wanted to make sure everybody understood that. Okay, I'd like to welcome everybody today to our Airflow and Duct Design Module 1 and 2. And so this is going to be a double session today, Module 1 and as well as Module number 2. And as we progress through the PowerPoint today, please make sure that you can see the screen clearly. If you can't see the screen clearly, be sure and unmute your mic and sound off. But we'd ask at this time everyone to go ahead and mute your microphone if you haven't already. And if you do have a call come in, please don't put us on hold. As a result, if you did, everyone would be able to enjoy your elevator music. So please be sure and mute your mic unless you have a question, and then by all means unmute your mic. In addition, throughout the day, we'll have the opportunity to unmute your mic when I come up to spots where it's a logical place for questions or comments. I'll just ask everybody at that time if they have any questions or comments, and then you can unmute your mic, and then away we go with our questions at that point. So today we're going to learn about airflow and basic duct design. And the subjects we're going to be talking about today will include the following. We're going to talk about and review the relationship of velocity, or the speed of the air, that's going to be measured in feet per minute, or also called velocity, and CFM. So there's a distinct relationship between how fast the air is moving down through a duct system and the amount of CFM that's being delivered. We're also going to have some practice sessions of CFM based on grill size and velocity, and we'll review and talk about some of the tools and the things that we'll need to measure airflow with the velocity method. So the first thing we like to start out with in our airflow and duct design class is we like to ask the question, what is CFM? Now, of course, the canned answer is cubic feet per minute, but as we really dig in, let's talk about what CFM really is. So CFM, or cubic feet per minute, is the amount of air in cubic feet coming out of an opening or moving through a duct system over a period of time. And this time is typically 1 minute. So when we talk about cubic feet, it's the volume of air that's moving through a duct system, or coming out of a duct opening or moving through a duct system over a 1 minute period of time. So we're going to have to look at some factors to calculate CFM by looking at the amount of air coming through the system and over a period of time. And so here's what we have to do. Two factors must be known to determine CFM. The first factor that we have to consider is the size of the opening, or the duct cross-section, in square feet. Now remember, team, we always have to get to square feet. So when we measure a duct, and we'll have the opportunity to do some practice sessions here. And so, by the way, everyone take your iPhone, or if you have a handheld calculator, and take your iPhone and go to calculator function, because we're going to have you doing some calculations just for practice. And so make sure that your iPhone is on calculator function, or if you have a handheld calculator, go ahead and use that. But we'll go ahead and I'll go to my iPhone as well in the calculator function, so we're all kind of on the same page of music. So again, two factors must be known to determine CFM. Number one, we have to know the size of the opening, or the duct cross-section, in square feet. Now to determine square feet, we're going to divide the size of our duct opening. We'll take a tape measure or a ruler, and we'll take that tape measure or ruler, and we'll measure the duct opening, or the cross-section of the duct, and let's say it's 12 inches by 12 inches. And so, okay, Jill, I see that you're saying we're not having some screen. Is that correct? Go ahead and unmute your mic and let's talk about it.
I didn't say anything, Joel. Mine's all good.
Okay, because I was getting a text field that, let's see here. I was getting a text message from you. It said screen. Are you logged in? Nothing is showing on my screen.
Oh, that was from earlier.
Oh, I'm sorry. Okay.
That was from before.
Okay. All right. Well, let's keep going then. Apparently, my phone was just now catching up, so that's that can happen. So back to our subject at hand. Thank you. So two factors have to be known to determine CFM, team. Number one, we need to determine the size of the opening or the duct cross section in square feet. Now remember, we always have to get to square feet. So what we're going to do, we're going to measure the duct opening in inches and then divide by 144. And so this division by 144 will always get us to square feet. So let's do an example. Let's say, for instance, we have a duct that's 12 inches by 12 inches square. So we take 12 times 12 and we divide by 144 and we see that that's 1 square foot. So number one, we always have to get to square foot on our duct section. Number two, we need to measure the velocity or the speed of the air coming through or moving through the opening or the duct in feet per minute. And so to find CFM with this formula, we find the square area opening or square foot opening or cross section of a duct, and then we measure the velocity of the air. Now it should be noted there's a couple different tools you can use to measure velocity. One of them is called a hot wire anemometer. A hot wire anemometer is a tool. It's actually a probe that you will drill a hole in the side of the ductwork, and then you'll slide this hot wire anemometer into the duct, into about the middle of the duct, and read the velocity of the air directly. Another tool is what we call a rotating vane anemometer. It's also called a rotating vane tool. And what it is, it looks just like a little wheel that whizzes around and around as the air passes across. It looks like a little fan that you hold in your hand. And so we can remove the register from the opening of the duct opening, or we can actually cut a hole in the side of the duct and we can put that rotating vane tool in there as well. So either method is good for measuring duct velocity, but by all means we have to find our velocity in feet per minute. So one more time, we find the square area of the cross section of the duct in square feet, step number one. Step number two, we find the velocity of the airstream in feet per minute, and then we simply multiply square foot opening times velocity, and that will give us the CFM we're actually moving through that section of duct. So as you take a look at our graphic, let's do a couple examples together as you clear your calculator or have your calculator function handy. So in our example, let's say we have an 18 by 36 duct. So if you take a look at the graphics on your screen, we see we've got a duct section down below there, just that gray rectangle that's representing a duct. And let's say it's 18 by 36. So if we take 18 inches by 26 inches and we multiply that together, we get 468 square inches. Now remember, team, we always have to get to square feet. So we take that 468 in our example and we divide by 144, and that equals a 3.25 square foot cross section of that duct, or that opening of that duct. Then what we need to do, that's step number one, so we have 3.25 square feet in our example. And then what we do next is we take the velocity of the air. Now you'll look at the graphic and you'll see that it looks like there's like a blue cubic foot hunk, or a blue cubic foot cube moving through that duct system. Now we know that air doesn't move in hunks or cubes like that, but we had to try to come up with some sort of graphic that made sense. So you'll see that in our example we have 3.25 square feet opening, and we're representing about 60 feet per minute velocity. As we see the graphic there, we see these hunks of air, if you will, moving through. Now we know they don't come through in hunks like that, but the point is it kind of gives a visual of the idea we're trying to get across today. So 3.25 square foot opening of the duct, we multiply that times 60 feet per minute velocity, and our CFM, if you take your calculator and you multiply 3.25 times 60, that will give us, in our example, a CFM of 195 or 195 CFM. Any questions or comments on that so far? Okay, well, let's speed that air up. We're not going to change the size of the duct, but let's just speed the air up to say 120 feet per minute. And we keep the same size duct opening, in our example 3.25 square feet. And we speed that air up to 120 feet per minute. We notice that we change the CFM if we take 3.25 square foot opening of the duct and we multiply it times the velocity of the air that we're representing of 120 feet per minute velocity. If we multiply those two factors together, we see that in this example, we haven't changed the size of the duct, we've just changed the speed of the air, and now we are now delivering 390 CFM at that faster airspeed rate, if you will. And let's do one more example just so everybody kind of gets the visual here. Let's speed that air up some more to this. This time we'll speed it up to 350 feet per minute. And we see that at the same size duct, if we speed that air up to 350 feet per minute, we're now delivering 1,138 CFM. And so this is a very, very important concept, team, that at any given duct size, if we have a particular duct size, at any given duct size, we can change the CFM, or the amount of air that's being delivered in cubic feet per minute, by speeding up the air or slowing the air down. Now this becomes very, very important later on when we start looking and we start designing a duct system, because there will be target velocities that Manual D is going to recommend when we build a duct system. Now, by the way, Manual D is kind of the Bible, if you will, for airflow and duct design. So I would highly recommend that if you desire to really learn more about airflow and to find out what Manual D says, ACA Manual D is the criteria that's set forth in our industry for designing a duct system. It's about a 1-inch thick manual, and if you'll Google Manual D, that's like Delta or dog, Manual D, if you'll Google Manual D, you can certainly purchase a ACA Manual D online for a more in-depth education as far as how to design a duct system. So we're going to be talking about basic concepts today with airflow and duct design, but please note this, that everything we talk about today is right out of Manual D. So everything, all of our criteria that we talk about as far as velocity and measurements and so on, is right out of Manual D. Any questions or comments before we continue? Okay, well, let's do some practice together. So let's say, for instance, we want to actually measure the CFM moving through a duct system, and in our graphic you see that you've got a what looks like a piece of ductwork in a 3D view, a long piece of ductwork 3D, and we also have a little arrow that's pumping and moving, kind of showing us the direction of the air. And so to measure airflow, or to measure CFM using the velocity method, step number 1, we need to measure the duct opening, length times width, to find square inches. Step number 2, we divide by 144 to find square feet. Now remember, team, we always have to get to square feet if we're going to measure airflow with the velocity method. We have to know the square foot opening, or the square foot cross section of the ductwork. Step number 3, we're going to measure the velocity of the airstream in feet per minute. Now what we show in our graphic, it looks like a little what we call a rotating vane anemometer, also called a velocity tool. It's just a little wheel that spins as the air goes across it. It should be noted that you could also use what we call a hot wire anemometer, which is nothing more than a probe. With a hot wire, you would poke a hole in the side of the ductwork and slide that probe in. Or you can remove the register or grill from the ductwork, and you can take this rotating vane tool and put it right in the ductwork, or right in front of the ductwork, and measure the velocity of the air either way. So whatever method you choose, they both work very, very well. But whatever method you choose, be sure that you're measuring velocity of the airstream in feet per minute. Then step number 4, we multiply velocity in feet per minute times the square foot opening, or cross section of the duct, to find the delivered CFM. So if everyone will please take your calculator and clear them and zero them out, and let's do some examples together. So let's say in our first example right here, if we take a look at our screen, we see we have a duct opening that's 12 by 30. We have a duct opening that's 12 by 30. So if we take 12 times 30 on our calculator, that should equal 360 square inches. Now hang on, team, we're not done yet, because we always have to get to square feet. Now to get to square feet, we are going to divide by 144. So we take 360 we divide by 144, and that's going to give us the square foot opening or the square foot cross section of this particular duct in our example. So we take 360 divided by 144, and you should come up with 2.5 square feet. So 2.5 square feet is the actual cross-sectional duct, the cross-section of that duct opening, or the cross-section of that duct where air is moving through it, 2.5 square feet. We then use the appropriate tool, either a rotating vane tool or a hot wire anemometer, to measure the velocity of the airstream. And in our example, we see that the velocity is 650 feet per minute. Now to find CFM, we're going to multiply those two factors together. We're going to multiply 650 times 2.5, and that will give us the CFM. So if someone has done that for me, let's go ahead, we'll make this a little bit interactive right now. So 650 feet per minute times 2.5 square foot cross section on the duct opening. How many CFM are we moving through that duct system at this time? Anybody? Okay, well, I've got a 1625 CFM would be the amount of CFM we're moving through that duct opening over that size duct. So 2.5 square feet is the size of the duct opening, and the velocity of the airstream is 650 feet per minute. And so in our example, 1625 would be the CFM we're moving through that duct in this example. Okay, let's see. Looks like we've got somebody chatting. 1625. Good. Thank you. Emily said 1625. Thank you. Okay, so as we continue looking at our PowerPoint, let's do another example or two together. So in our next example, we have a duct opening, or a cross section of a duct that's 14 by 22. And so we multiply 14 times 22 on your iPhone or your calculator. You'll see that gives you a square inch area of 308. But now remember, team, we always have to get to square feet. So we're going to divide 308 by 144. So divide 308 by 144. And that will give us the square foot opening of the ductwork. So in our example, it's 2.1 square feet. 2.1 square feet. And then we'll then measure the velocity of the airstream. And in this example, it's 745 feet per minute. 745 feet per minute. Then to find the CFM, we're going to multiply the feet per minute in our example, 745, times the square foot opening, or the square foot cross section of the duct, which is 2.1. So we then multiply 745 feet per minute times 2.1 square feet cross section, and that will equal a CFM of 1565. So team, it's really important. We can always take the cross section of a duct, find the cross section in square feet, measure the velocity of the air, and find CFM, actual CFM moving through that section of duct. Well, this becomes really, really important, especially when you're commissioning a system, or if you want to confirm that a section of duct is delivering the CFM required. So again, the tools that you'll need will either be a hot wire anemometer, also just called a hot wire velocity tool, or the rotating vane tool to find velocity. So from a point of explanation, the method that we're using for measuring airflow is called the velocity method. The velocity method. All right, let's do another example. Just to make sure everybody's got this, we'll pick up the pace a little bit. So clear your calculator for me. We have a 10 by 16 duct in this third or fourth example. A 10 by 16, which gives us a square inch opening. 10 times 16 is equal to 160. We then divide 160 by 144, because remember, team, we always have to get to square feet. And the way we do that is we divide by 144. So we divide 160 by 144 to find our square foot opening. And in our example, 160 divided by 144 equals 1.1 square feet. So that 10 by 16 duct actually has a square foot cross section of 1.1 square feet. We then take our velocity tool and we measure the velocity of the airstream in feet per minute. And in our example, we see we have 825 feet per minute velocity. We then multiply those two factors together to get CFM. So 825 feet per minute times 1.1 square foot duct opening or duct cross section. The actual CFM moving through that section of duct at that point of measurement is equal to 908. So that 10 by 16 duct is able, at that 825 velocity, is able to deliver 908 CFM. At this time, team, go ahead and unmute your mics if there's any questions or comments so far. We're going to do one or two more examples. We'll do some round duct examples, and then we'll move on to something else. Is there any questions or comments at this time? Okay, well, let's move on then. So if we're dealing with a round duct, now oftentimes when we are out on a job site or when we're setting up a duct system or designing a duct system, oftentimes we'll use round duct because it's readily available. It's also more efficient because you actually use less sheet metal to get a particular cross section of duct. And so round duct is actually a very, very good material. And to find the round duct cross section, we need to apply a little bit of math. And so we remember in our high school days and probably grade school days when we learned some basic geometry, we know that 1/2 the diameter of a round duct or circle is called the radius. And so if we apply a little bit of a mathematical formula, if we take the radius, which is 1/2 the diameter of the ductwork, if we take the radius times itself times a mathematical constant for finding square area, 3.14 is also called pi, if you remember in your basic math days, pi, 3.14. And by the way, that 3.14 is a number that goes out in infinity and never repeats itself, does not repeat itself. But for all practical field purposes, 3.14 is all the farther you need to take that mathematical constant for finding the area of a circle. So again, the radius, or 1/2 the diameter of the circle, or the round duct, times itself, times 3.14 will equal the area in square inches. Now remember, team, once you get square inches, you still have to divide by 144 to get square feet. We always have to get to square feet to use this velocity method for measuring CFM. So let's do an example or two together. Let's say we have a duct opening that's 16 inches. 16 inches. Well, if you want to clear your calculator, you're going to find that a 16-inch round duct has a radius of 8 inches So we take the radius times itself. In our example, 8 inches, 8 times 8 is equal to 64. But now remember, we have to multiply it times that mathematical constant of 3.14. So we take 64 times 3.14. And that gives us a square area of about 201 square inches. Now remember, team, we always want to get to square feet. So we then take that 201 and divide by 144 to get to square feet. And if you'll go to your calculator, please, and do that for me. 201 divided by 144 is equal to a square foot area of about 1.4. So 201 divided by 144 is equal to 1.4 square feet. Now, team, you'll notice on your calculator it may be 1.395872334, whatever. Just round up or round down. So round to the nearest digit. That's plenty close for field work. So 1.4 square feet is equivalent to a 16-inch round duct, about 1.4 square feet. Then we do the same thing as we did before. We take the velocity of the airstream. And in our example, we're showing that we have a 725 feet per minute velocity on the airstream moving through that duct section. And just like we did before, we multiply the velocity times the square foot area to get the CFM. So if we multiply 725 times 1.4 square foot area, we see that 16-inch duct is at that velocity is delivering about 1,015 CFM. Now, team, this is really, really important. One of the things that we find in the industry is quite often contractors, they have undersized ductwork. And if you have undersized ductwork, the system cannot perform. It doesn't matter who manufactures the equipment. If you don't provide proper airflow, the system will not be able to deliver the capacity it's designed for into the conditioned space. Now, please write this down or make a note of this. We always want to design our ductwork. We always want to design our ductwork to provide 400 CFM per ton of cooling. So one more time, that's 400 CFM per ton of cooling. So if we have a 2-ton unit sitting outside, we have to design our ductwork to carry a total of 800 CFM. If we have a 3-ton unit sitting outside, we have to design our ductwork to deliver 1,200 CFM into the conditioned space. So 400 CFM per ton of cooling capacity of the outdoor unit is the criteria that we want to always design our ductwork to, 400 CFM per ton. So in our example here, we see that 16-inch round duct is actually good for about a 2.5-ton unit, based on 725 feet per minute velocity. So remember, team, it's important that we always design our ductwork based on manual D recommendations, and we'll get into velocities and recommended velocities in a little while here. But at this point in time, we just want to make sure everybody understands this relationship between CFM and the velocity of the airstream. Any questions or comments so far? Okay, well, let's do one more example of round ductwork, and then we'll move on to something else. In our second example here, it looks like we have a duct opening of 14 inches. 14 inches. So let's take the radius of that 14-inch duct. That's 7 inches. So 7 times 7 is 49 times 3.14 should give us a cross section of 154 square inches. Now, team, remember, we always have to get to square feet, so we're going to divide this 154 in this example by 144, and that 14-inch round duct has a square foot cross section of 1.07. 1.07 square feet. We then measure the velocity of the airstream In our example, where we see we have 810 feet per minute. We then multiply the velocity in feet per minute, 810, times 1.07 square foot cross section of the duct. And we see in this example that 14-inch duct at 810 feet per minute velocity is actually delivering 867 CFM. So in this example, if we design our duct system at 800 feet per minute velocity, this section of trunk right here, let's say this is the main trunk, would be good for about a 2-ton unit. So it's important, team, we always look at the velocity or the speed of the air, because manual D, we're going to learn in a little while, manual D actually sets forth a recommended velocity in each section of ductwork. It's going to recommend a particular velocity for the main trunk. It's going to recommend a velocity for all the takeoffs. It's going to recommend velocity through registers and grills. So it's important that we have this concept that CFM and velocity are tied hand in hand when we're designing a duct system. Let's do one more round duct formula just to make sure everybody's got this, and then we'll move on to something else. So clear your calculator for me, please. And this final example, we have a 22-inch round duct. A 22-inch round duct. So the radius of a 22-inch round duct is 11 inches. So we take 11 times 11. And then we multiply that times 3.14 to get the square area. And so in our example here, it looks like we have about 380 square inches on a 22-inch round duct. 380 square inches. We then divide that by 144, and that should give us our square foot area of that 22-inch round duct. So we take 380 and divide by 144, and that gives us 2.64 square feet. 2.64 square feet. Then what we do, team, we take our velocity of the airstream. In our example, it's 760. So we have the velocity of the airstream is 760 in our example. We then multiply 760 times the square foot opening. In this example, 2.64. And once we multiply 760 times 2.64, that's going to give us a CFM of 2006. So that 22-inch round duct, 22-inch round duct, based on 760 feet per minute velocity. Let's say this was the main trunk on a unit. It would deliver 2,000 CFM, a little over 2,000 CFM, which would be good for a 5-ton unit. So think back, team, on some of the jobs maybe you've been on, or some jobs you've seen. And think back on the size of duct that you've seen on a main trunk, for instance, on a 5-ton unit. We see that at this velocity, at 760 feet per minute velocity, if that's an acceptable velocity with manual D, it takes more like about a 20 or 22-inch round duct to provide 5 tons of airflow. So if you get out on a job site, especially if you're also an inside support specialist at your company, at your wind company, and you get out on a job site, or you have the opportunity to look at a job and you see that you've got a 16-inch round duct or maybe an 18-inch round duct on a 5-ton unit, it's not sufficient to provide the adequate airflow for a 5-ton unit. So just keep in mind, remember, you have to have proper airflow, 400 CFM per ton at the proper velocity to deliver the capacity of the unit into the conditioned space. Any questions or comments on this basic concept of airflow, CFM, and the velocity through a duct system? Any questions or comments? Okay, so let's say, for instance, we have a free area of a register and a grill. This is something very, very important that we need to recall, that you're not going to have just a raw duct opening. going into a space. You're going to have some sort of grill or register over that duct opening. So once we put a grill or register over the end of that duct, we're going to change the dynamics of the air coming through that grill or register. And so it's important that we know that by putting that grill or register in front of a duct opening, you're going to change the airflow, you're going to change how that air is moving and how that air is distributed into the conditioned space. So we need, at this point, we're going to take put a little bit of a formula on how to find the free area of a grill or register. So the free area of the grill or register takes into account all the slats of that grill or register that's actually in the airstream as it moves through that grill or register. So to find the free area of a grill or a register, you're going to measure the grill or register opening and convert to square inches just like we did before to square feet. So we measure the grill or the register opening where the air can actually move through that grill or register. We then divide by 144 to get square feet just like we did before. And then we multiply that number times 0.8 to get 80% to obtain the free area. So this is important because a register or a grill sitting in front of a duct opening is going to restrict about 20% the amount of air that's moving through it. So we can always figure a good solid field number is a quality designed grill or register is going to deliver about 80% of the air that's actually behind it or in front of it. And that's a good solid field number. So let's do some examples together. Let's say we have a 20 by 30 grill. And so we take 20 times 30. This is where the air can actually move through that grill now. You've measured it and you've looked at it. And the air can actually move through that grill at 600 square inches. We then take that 600 square inches and we divide by 144. And in our example, we have 4.16 square foot opening. However, we have to take into account that that grill is only going to be about 80% efficient. So once we divide by 144 and we get our 4.16 square foot opening, we now divide that by 0.8 to account for that 80%. And then we see that our actual grill or register free area, what we call free area, is actually 3.3 square foot free area of opening. Any questions comments on that so far as we take a look at free area registers or grills? Okay. Well, let's do a couple examples then of looking at the free area and the velocity or the CFM going across to a grill or register. So in our first example, what we're going to do, we're going to measure the grill and convert to square inches. And then we're going to divide by 144 to get square feet. We'll then multiply times 0.8 to obtain the free area. And so let's do that. So let's say we have a 24 by 30 grill. 24 by 30. We multiply 24 by 30 and we get 720 square inches. We then divide by 144 just like we did before to find square feet. And so in our example, a 24 by 30 grill, divide by 144, that gives us 5 square foot opening. But now hang on a second, we have to multiply times 0.8 to get the free area. So we take 5 square feet and multiply times 0.8. And that actually gives us a 4.0 or 4 square foot free area. Now, team, what we're going to do, we're going to divide that grill or that register into 4 to 12 equal test areas because we're going to average the velocity across that grill. So clear your calculator for me. And we're going to add all of the different areas of that grill. We're going to take velocities across the areas of that grill. Then we're going to add them up and divide by the number of test areas to get an average velocity across that grill or register. So clear your calculator for me. We're going to start taking velocities in those segments that we've segmented across the face of that grill or register. We'll then take the average velocity and then multiply it times the free area of the grill to obtain our CFM that we're actually moving across that grill or register. So you're going to be finding that a rotating vane tool or velocity tool can be used more than just measuring airflow in a duct system. You can actually measure the airflow across a grill or register as well. So clear your calculator for me, and our first reading is 325 feet per minute. And then add the next reading on your calculator. So 325 plus 355 is our next reading. Plus 402 is your next reading. Plus 395 is your next reading. Plus 325 is your next reading. Plus 485 is your final reading. So we see that we've taken 6 readings across the face of that grill, and we're going to take those readings and we're going to add those numbers together. 325 plus 355 plus 402 plus 395 plus 325 plus 485. We add those numbers together and we divide by the number of readings we've taken. In this example, we've taken 6 readings, so we take those numbers and add them up and divide by 6 for an average velocity across that grill of 381.2. We then take that 381.2 average velocity across that grill or register and multiply it times the 4.0 square foot free area of the grill or register. The result of that will be the CFM across that 24 by 30 grill. So in this example, we see that 24 by 30 grill at 381 feet per minute average velocity gives us a delivered CFM of 1525. Now it should be noted, if this is a filter grill, Manual D will recommend a certain velocity across that grill if it's a filter grill. If it's a return grill, it's going to recommend a different velocity, and we'll get to all that in a little bit. And if it's a register, if it's a supply register, it'll be a different velocity yet. So based on the grill or register that you're looking at, and based on if it has a filter behind it or not, will determine the velocity that's going to be recommended across that grill or register. Any questions or comments so far? Okay, team. Well, let's go ahead and do one more example, and then we'll get into something else as we move through our airflow and duct design class. So in this second example, again, we're going to measure the grill and convert to square feet and multiply times 0.8 to obtain free area. So in this example, we have a 30 by 30 grill, 30 by 30. So if we multiply 30 times 30, that's 900 square inches. Now remember, team, we always have to get to square foot area and free area on a register or grill. So we then divide 900 square inches by 144 to get square feet. This example, 6.25 square feet. But now remember, we have to take into account 80% efficiency on that grill. So we take that 6.25 square feet and multiply times 0.8 to get a free area of 5 square feet. So that 30 by 30 grill actually has a free area of 5 square feet that air can actually move through. We then divide that grill into 4 to 12 equal test areas like we did before. Now go ahead and clear your calculator for me. We're going to add the velocities and divide by the number of test areas to get an average. And then we'll multiply the average velocity by the free area of the grill to obtain the actual CFM moving across that register or grill. So clear your calculator for me. Our first reading is 320 feet per minute. Plus our next reading of 330. Plus our next reading, 320. Plus our next reading, 325. Plus our next reading, 340. Plus our next reading of 315. Now team, whatever that big number is, you've added those numbers together. You now divide by 6 because we took 6 readings. You divide by 6 to get an average of 325 feet per minute. We then multiply that average reading of 325 times the 5.0 square foot free area opening of that grill. And so in our example, let's say this was a return grill, 30 by 30 return grill. Under these conditions and the average velocity that we've measured across it, we see we're actually moving 1625 CFM in our example. So we can use our rotating tool, our rotating vane tool or our velocity tools to not only measure the velocity of a duct opening, or we can actually open up the duct and actually take the velocity that's inside the duct, or we can actually go to the register of the grill and we can measure the amount of airflow that's going across or through a register or grill by using this velocity method with the rotating vane tool and measuring the grill or register and measuring the velocity to find CFM. So team, is there any questions or comments on how we're utilizing a rotating vane tool and velocity and the relationship between velocity and CFM before we move on to our next subject? Any questions or comments? Go ahead and unmute your mic at this time if you have any questions or comments. Okay. Well, at this time we're going to we're going to jump into our airflow and duct design module number 2. And what I normally like to do at this point is give everyone the opportunity to stretch or if they need to. So if you'll go ahead and unmute your mics at this time, does anyone need to take a quick break, or should we go ahead and continue with module number 2 to push on through the rest of the day? Okay, team, well, I'll tell you what, then let's go ahead and continue with module number 2 on our airflow and duct design module number 2. So, we'd like to welcome you to this module as well. Today we're going to be learning, again, about airflow and duct design. And the subjects we're going to talk about at this time is going to be specifically, will include the following. We're going to review the air duct calculator. We're going to use it to find required CFM for different size units. And then we're going to also review return and supply duct sizing based on Manual D recommendations. So this is very, very important, understanding how to use the duct calculator, but also understanding that all of the information that we apply to building and designing a duct system is going to need to comply with Manual D recommendations. So everything we talk about today will be based on Manual D. As a matter of fact, the duct calculator itself is actually a Manual D duct calculating tool. And so if you'll take your duct calculator at this time, we're going to go ahead and look at some of the features of that duct calculator, and we'll see how we can use that to start designing and start getting a relationship of velocity, CFM, friction loss, and so on the duct calculator as we start to talk about and think about designing a duct system in Module 2. So, using the duct calculator. If you'll take a look at your screen at this time, and the duct calculators that we're featuring in our program today are just a real simple duct calculator. Happens to be one that we recommend for our schools, and hopefully you're able to get some of these duct calculators so that the information that we look on here together will be the same on the screen as what you have in your hand. So take your duct calculator at this time. Now, it should be noted if you have another brand of duct calculator, if you have a slide calculator or another brand of duct calculator, the information is going to be the same. It may be displayed a little bit differently than the one that we have on our screen, but by all means, if you have a copy of the one we have on our screens, you can follow along exactly. But if you have a different brand of duct calculator than what we have on the screen, by all means, find the information on your duct calculator that's equivalent to the information on the one we're displaying on the screen. So every duct calculator that I've ever seen anyway is going to have a relationship of velocity and CFM, just like we talked about in our previous session in Module 1. So on the duct calculator, you will find they will give you a chart that's going to allow you to find velocity in feet per minute and CFM. So if you'll take that duct calculator and if you line up any given target velocity and any desired air volume in CFM, if you move to the opposite side of the duct, it will tell you what size round metal duct will provide that air volume in CFM at any given velocity. So as we take a look at our example right here, we see that if we line up 500 feet per minute velocity in our example on the screen, and we line up 500 cubic feet per minute air volume, so in other words, if we line up the two 500s, in other words, 500 feet a minute velocity and 500 CFM, we see that it's going to take about a 12.5 inch, well, they don't make a 12.5 inch duct, so it's going to take, looks like a 13.5 inch duct. Well, they don't make a 13.5 inch duct, but they do make a 14 inch round duct. So you always want to round up in that example. So in our example, if I am designing a duct system around 500 feet a minute velocity in a particular duct section, and I need 500 CFM, I'm going to need a 13 inch round duct. Any questions or comments on that? Okay, well, you can also see in the same example by lining up velocity at any given velocity. If you'll take your duct calculator at this time and hold your duct calculator in your hand, and if everyone will take 700 feet a minute velocity, if you'll find 700 feet a minute velocity on the velocity scale, and it's 700 feet a minute velocity, let's say we're designing for 1,000 CFM, cubic feet a minute air volume. So if I take velocity, 700 feet a minute on our duct calculator, and 1,000 CFM, somebody help me out. What size round metal duct would I have to have at 700 feet a minute velocity and 1,000 CFM? Unmute your mic and somebody answer that for me, please. Go ahead.
Oh, 16-inch.
Is someone there? Hello? Good, good. 16 inch.
Dietrich
So
did.
thank you. And who just unmuted their mic for me? Okay, good, excellent. Well, thank you for that. So basically, team, what we're looking at, anytime we're looking at our duct calculator, we're able to find a particular round duct size based on velocity and air volume, required air volume. Let's do one more just for fun. Let's say we're designing a duct system. Let's keep that 700 feet a minute velocity. And so let's say we're designing a duct system around 700 feet a minute velocity on the main trunk. And we need 2,000 CFM. 2,000 CFM, let's say it's on a 5-ton unit. So 700 feet a minute velocity and 2,000 CFM. What size duct would we need to provide that? Anybody? Okay, we see at 700 feet a minute velocity at 2,000 CFM air volume, we would need an approximately 22-inch round duct to provide that air volume at 700 feet a minute velocity. So those two components on the duct calculator are very, very important, team, especially when we're designing a duct system based on Manual D recommendations, because Manual D will always recommend a particular velocity in a particular duct section based on the application of that duct section, whether it's a main trunk or whether it's a takeoff or whether it's a register or a boot and so on. So there's going to be recommended velocities that we're going to have to deal with according to Manual D. So we see that at any given velocity and feet per minute, in feet per minute, and air volume in CFM, if we line those up on the duct calculator, it will give us a round metal duct size. Now, if you'll take your duct calculator and take it back to where we had it a minute ago, where we lined up in our example on our PowerPoint screen of 500 feet a minute velocity and 500 CFM air volume, we see we need about a 14-inch duct, about a 14-inch duct. Now, the third component on the duct calculator is going to be equivalent duct size. So we see that a 13-inch round metal duct would work in our example on the screen, but let's say, for instance, we had some sort of construction constraint and we couldn't get a 13-inch round metal duct in there. So we can always fabricate a duct that will give us equivalent round duct dimensions as far as airflow capacity. So in our example, we needed about a 13.5 or 14-inch round metal duct in our example on our screen, but we see if we had some sort of construction constraint, we wouldn't be able to, maybe we couldn't get a 14-inch round duct in there. But if you look at my cursor moving on the screen right here, you'll see that let's say I could fabricate a duct 20 by 7 inches. 20 by 7 or 20 by 7.5 inches would give me the same equivalent as that 14-inch round duct. Or maybe a 10, if you take a look at my cursor, maybe a 10 by 15. About a 10 by 15 would give me the same equivalent airflow. So it's important that we understand the duct calculator not only gives us a velocity and CFM relationship, it'll give us a round metal duct diameter size to deliver that CFM, but it will also give us an equivalent rectangular duct size in case we have some sort of construction constraint and we can't get the round duct in there. So we can, in our example, a 10 by 15 or maybe a 20 by 7.5 would give us an equivalent airflow capacity of that round metal duct in our example. So is there any questions or comments from anyone concerning the information that we've discussed so far on the duct calculator? Any questions or comments? Okay, well, the final component we're going to look at on the duct calculator is what we call friction loss per 100 feet. And the friction loss per 100 feet will always give us the capability of finding out how much static pressure that duct system will build up against our fan based on the friction loss of that ductwork. So we can see that at any given air volume on top, if we take our duct calculator, we can see that at any given air volume on top, if we move that duct calculator, at any given size ductwork, at any given velocity that we've discussed before, we can see that the calculator will also give us the friction or the amount of static pressure that duct system is going to resist airflow per 100 feet of duct. So let's go back to our example on the screen just for fun and line it up to where we see it on the screen. We have 500 feet a minute velocity. We have 500 cubic feet a minute airflow, air volume. And in our example, we realized we needed about a 14-inch round duct or its equivalent. And then if we go to the very, very top of our duct calculator and we find air volume in CFM. So we see that we're dealing, in our example, with 500 CFM of air volume in our example. And we see that that 14-inch round metal duct at 500 feet a minute velocity and 500 CFM will give us a friction loss per 100 feet of approximately a 0.035, a 0.03 to a 0.035 friction loss per 100 feet. So if you were to take a magnehelic gauge, a very, very accurate type of water manometer, if you were to take a magnehelic gauge or a digital manometer, and you had 100 feet of 14-inch duct stretched out, and you were blowing 500 CFM through it at 500 feet a minute velocity off that fan, and you went to the outlet of that fan, and you put a static pressure probe at the outlet of that fan, and that duct was 100 feet long, blowing air through that duct 100 feet long, it would provide a static pressure against that fan of approximately 0.035 to 0.032 inches of water column static pressure. So this friction loss per 100 feet is a very, very important aspect of our design because we want to make sure that as we build a duct system, we do not exceed the static capability of the fan. And so when we start looking at actually designing a duct system, we want to make sure that all the duct components that we put on there, all the ductwork and all the takeoffs and all the registers and all the dampers and all the filters and all the different things that we build into a duct system to complete a system, to build a complete system, we want to make sure that we are aware that the friction loss of that ductwork and the friction loss of the boots and the friction loss of all the components of that duct system do not add up and exceed the capability of the fan. And so this is one of the issues that we see a lot of in the field team, is the fact that contractors will build a duct system, but they do not take into account the velocity or the CFM that's being delivered in that duct system, and then the ultimate check and balance, if you will, the friction loss that that duct system is providing against the fan and static pressure. And so we'll learn more about static pressure in our future modules. Next week we'll be getting into module number 3 and 4, and we'll learn more about static pressure and taking static pressure readings to determine airflow on a duct system. In addition, we'll also be looking at building a duct system in module number 3 and 4. But today's sessions, we wanted to review CFM and feet per minute, air velocity and CFM, and we also wanted to review the duct calculator in this session. So please unmute your mics at this point in time if there's any questions or comments on the duct calculator and the basic information it's giving us, and the importance of being able to look at those components, specifically velocity, air volume, rectangular duct size or round metal duct equivalent, and friction loss per 100 feet of any given duct size as we apply that ductwork on our systems. Any questions or comments? Well, team, we talked a little bit about recommended duct velocities. One of the handouts that you should have with your handouts or your book is a velocity table. So this recommended duct velocity table that is part of your handout package shows that there are recommended velocities of specific duct components on the supply and the return side. So as we start building a duct system, we need to definitely consider these factors when we build a duct system. So let's review our velocities tables. And again, this is all based on ACA Manual D. This is right out of ACA Manual D, this velocity table. So we see that on the main trunk, so the main trunk would be our main ductwork or the main trunk where all of our branch ducts come off of. This is what's going to come directly off the equipment, the main trunk. And so we see that on the supply side of the main trunk, Manual D recommends 700 feet a minute velocity and a maximum velocity on the supply main trunk of 900 feet a minute velocity. On the return trunk, on the return trunk going back to the equipment, it's recommended 600 feet a minute velocity and with a maximum of 700 feet a minute velocity on the return trunk. On the branch ducts, now team, that's all the takeoffs. The takeoffs coming off the main trunk, going to all the different rooms and spaces. The recommended velocity on a branch duct is 600 feet a minute velocity with a maximum of 700. And the return takeoff or the return branch coming back from the rooms back into the return trunk is 400 feet a minute velocity with a maximum of 600 feet a minute velocity on the return system. Now our registers and our grills are the same. You'll see that the registers are 500 feet a minute. Velocity, that gives us adequate on the supply side. The register gives us 500 feet a minute velocity. That gives us adequate throw into the space with a maximum of 750. And what I normally recommend on registers is to go somewhere in between. That way you have adequate throw, but you also do not have excessive noise. Now watch this. This is really important on a return register. Return registers, it's recommended 400 feet a minute velocity and with a maximum of 600 feet a minute velocity on a return grill or register. We see that our diffusers and our grills and registers, they all have the same basic recommendations as far as on the supply and return side of those velocities. As you look at your Manual D recommended duct velocity table, you'll see that diffusers, grills, and registers have the same criteria. Now this is really, really important, team. At the very bottom of your ACA Manual D velocity table that we've given you for a handout, or that you've printed out as a handout, it should be noted that if you have a filter grill, in other words, if you've got a return grill with a filter in the grill, the maximum recommended face velocity across that filter is 300 feet a minute on the return. So this is really important that when you're sizing your return grills, you want to make sure to account for if you've got a filter in it, you don't want to exceed 300 feet a minute with a filter. But if you have a return grill without a filter in it, that 400 to 600 feet per minute is the recommended velocity across those return grills if there's no filter in it. But if there's a filter in it, you do not want to exceed 300 feet per minute across that filter. That's recommended Manual D. So any questions or comments on the velocity tables that we've provided for Manual D as we start looking at some of the specific components, main trunks and branch ducts and so on, as we've discussed in this session? Any questions or comments on that? Okay. Well, team, is there any questions or comments? Let's go ahead and open the floor up as we are concluding our session number 1 and 2 today. Airflow and duct design session number or module number 1 and 2. Is there any, go ahead, everyone, if you'll please unmute your mics at this time. Let's open the floor up. If there's any questions or comments on what we've discussed today, go ahead and open your mic at this time and we'll answer those questions for you. Okay, well, team, at this time, we'll go ahead and conclude Module 1 and 2 for our airflow and duct design. I want to thank everyone today. Thank you kindly for your attendance. And we will look forward to training with everyone again next week at the same time and station, if you will, same time and station, as we conclude our training for today. We'll go ahead and conclude the meeting, and if there's no further questions, we will see you next week
No, I just said thanks.
at the
Good
same
job.
time for module number. Yes. Yes. Oh, okay. Well, thank you very much, and thanks everybody again for attending, and we will see you next week at the same time and station. Have a great week.